Up to now, all you've known is there's some sort of magical friction force that basically slows things down, right? And I'll say that force is 2 newtons or 5 newtons or whatever. And what all you ever really have to do is include it, add it as a negative, and move on, right? So it's not really that big of a deal. So I'm going to sort of expand your knowledge base a little bit, sort of go to that next step, and discuss a little bit more about friction in general. Like that one?
Yeah.
Yeah.
Huh. He's putting them everywhere. I didn't get that. Give me a second on that one.
A guy dumped chocolate milk all over me today at lunch. I said, how dare he?
Dairy.
Oh,
All right. As always, your choice as to just how much you want to write down. I'm summarizing that reading for you. If you feel at the end of this you need a little bit more info, or you need to sort of expand or get a deeper sense of what's going on, then you should do the reading. I will be recording these as well. Facility later. Posting. Okay. So, friction is a force that resists motion. It involves objects. Friction is a force that resists motion, and it involves objects that are in contact with each other. There must be contact. And more often than not, there is a force that is pushing those together, and usually, Johnny, it's gravity. Okay, so some causes of friction. What really is going on here? Type of thing. Scientists believe that an object will deform a surface and vice versa. In other words, when you put this book on the table will actually sort of create a little depression, kind of a little hole. Okay, so I will also say that friction isn't overly well understood. They're still sort of looking into it. So there's this little depression, this little hollow, and some scientists believe that a plowing force is required to move the object over the deformations. I would argue that it's almost like a type of, you're working against gravity, right? Like you're kind of going uphill all the time. You've got this microscopic kind of depression, so you're sort of going uphill. This one is pretty much understood. Irregularities, little bumps, interlock and offer resistance to movement. Okay, like it's like a rough road. What we see as a smooth tabletop is actually, hills and valleys, and whatever's sitting on top would be the same. And you see that, like for example, if you're sanding wood, right? Like your sandpaper is rough, and when you're done sanding, your sandpaper is not so rough, and neither is the wood, right? So what's happening? You're creating sawdust. You're taking off that. You're smoothing it down, making it smoother, flatter. There are some people that believe that as you get closer to that perfect smoothness, that actually the resistance actually increases. Why do you think that might happen? Like as it gets so incredibly smooth. But there's less of them altogether. Yeah, it actually creates a vacuum leak. That's right? There's no air in between, and so the pressure, outside pressure, actually holds it in place. Kind of like when you take like a suction cup to the wall, right? Not only that, but the molecules themselves are getting very, very close. You're getting an intermolecular attraction, that type of thing. Yeah, I think they do believe that. Like it's still a sort of a ongoing investigation. These sort of causes are more just sort of general interest. I'm not really too worried about this kind of stuff. These are, I'm not sure how these got, I'll have to fix these notes. There's two types of friction. There's what we call starting friction, and you'll notice that I've highlighted the word maximum.
Starting or starting?
Starting. It's actually both. Starting friction is also known as starting friction. Or sorry, static. Yeah, starting is known as static. Yeah. Starting friction or static friction is when the object is at rest. So when I go to push the hole punch, it's at rest, right? When I go to push it, that initial sort of force that you need has to overcome what's called static friction. Static means something at rest, like static electricity, the opposite of current electricity. Yeah, just there, not moving. The opposite of starting friction would be sliding friction. And in a more technical standpoint, that's referred to as kinetic friction. And that is the frictional force between objects that are sliding with respect to each other. For sure, this is something that you will need to know, that kinetic friction, sliding friction, is always less than static friction. Actually, I should say not always less than or equal to, actually. So starting friction is the maximum friction force. It's that maximum amount of resistance. And once you get something going, it's actually that amount of friction is reduced a little bit. Sometimes they are equivalent to each other. So you should be familiar with those two terms, static friction and kinetic friction. Yeah, all good? Oh. Okay, so some overall properties or characteristics or background material that you need to be aware of. Friction acts parallel to the surfaces that are in contact, the key word being parallel, and in the direction opposite to the motion or to the net force tending to produce such motion or trying to produce that motion. So it's always opposite the motion or the intended motion. And you can probably summarize that a little bit if you want.
Is there frictionless surface?
They try to get frictionless. Things like an air hockey, you know what an air hockey table is with? When you got that table with the air pushing up, so they try to reduce friction considerably. Things like stainless steel on ice is quite frictionless, but they can't quite get it down to like 0. Yeah, almost approaching 0. Skates? Yeah.
Skates actually don't.
When you slow down after a while, like
Hey?
Skates actually don't physically ice.
In the front? Yeah. On the water? Yeah, that's kind of what a current rock does, right? A microscopic layer of water, yeah. That's another thing I guess you should be aware of with friction too, is that sometimes we want friction, and sometimes we try to reduce it. Can you give me an example of where humans try to reduce friction? Something a little more practical. What's an example where you want to reduce friction?
Flying.
I suppose flying, yeah, you're trying to be more aerodynamic. Think about the Olympics, right? Like maybe the swimmers, the suits they wear, or the runners, the cyclists, the helmets they wear. But something that you all rode in today, in an engine. What do you put in the engine to reduce friction? Oil, right?
Like when they shave your armpits because it slows it down. Not just the armpits, the whole body. It
The
does.
swimmers. Oh yeah, the swimmers. Yeah. Shave. Yeah. That's why they wear the caps. Some of the guys shave their head. That's why I do it, to reduce friction. There's another reason? Yeah. Keeps me up to speed. Can you give me an example of where we try to add or encourage friction?
Papers.
Where? Yeah, tires, or when they go out in the wintertime and they throw sand down on the
I
streets.
just said a cold.
Yes, you said that's for reducing.
Yeah, well, you want your tires to be like.
Yeah, you do, so that way you can stop that.
Yeah, you want to increase friction at stop
We're
signs.
trying to gas it. can't go up.
Yeah. It depends on what you're trying to do, I guess, right? Okay, so here's an example. Here's a picture of applied force, friction force, right? Always opposite to the motion, and always parallel. So, like, if it's at an angle, right, then friction is parallel to the surface. It forms the shape, goes in the same direction as the ramp. Now, friction depends on the nature of the materials in contact and the smoothness of the surfaces. The smoother they are, the less friction until you get to a certain point. Okay? Doesn't say anything about surface area here, does it? It just says that friction depends on the nature of the materials in contact and the smoothness of the surface. How smooth they are. I'll get to that. Brett, what's the difference between a Teflon slider and a stainless steel slider? One's faster. What do you mean by faster? Which one has less friction? Stainless steel, right? I've curled with a stainless steel slider and a Teflon. The stainless steel is incredibly slippery.
Oh, and
Yeah.
if you like raise your butt, you go way faster because you're.
When you're curling?
Well, no, when you go down the slide,
Oh, okay. Yeah.
like a water slide.
Well, you go on one side, you go like this, right?
Yeah.
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 Yeah, it's debatable there. I've certainly done that. Junior?
If the friction is opposite, it means that always the object is gonna be stopped.
No, it could be opposing the motion, like if it's already moving, it's opposite the motion, but if it's not moving, it's still this way, right? Like, if there was no friction and I could push the desk that way, friction would be this way. But friction is more, right? I can't overcome it, so it's still the same direction. Now, I think I said this already, sliding friction is less than or equal to starting friction. Keep in mind it can be equal. I think that's actually been a test question in the past. They can actually be equal, yeah.
So like how? Even if you're pushing it, it's the same.
It's the same. It's the same at the start as it is as it moves. Okay. Now, friction is practically independent of the area of contact, and this is hotly debated. Leo's brought it up already. You know, he said when you lift your butt and you go down the water slide, you just kind of on your shoulder blades. You do tend to go faster, don't you?
Yeah.
You do go fast.
You do, yeah. I've done it, right? It might be just something to do with less water resistance, that type of thing.
What was your underwear? I don't know how you call
Your
it.
bathing suit?
Yeah.
Yeah,
It doesn't have friction on that. So.
that's true. Yeah. So maybe it's because instead of sliding on the fabric of your bathing suit, you're sliding on the smoothest surface of your skin. That could be.
There's your shoulder blades.
Yeah. Yeah. There's a lot at play here. But for the most part, friction is practically independent of area of contact. A lot of people get confused by this. They see the great big giant tires on drag cars, right? And that's more about reducing pressure so that it doesn't heat up as much so that they don't have to replace the tires as often. Yeah, that is pretty cool. You're right. How come, like those big drag tires or the racing tires, how come they don't have a tread on them? Like, how come we ain't got treads on our tires?
We have it because of the
Yeah,
rain.
for water.
That's why. You could drive around on a normal day with bald tires. The problem is, we have to drive in the rain. We have to drive in the snow, right? And ice. When they're running those cars in NASCAR, they don't run in the rain, or not a lot.
That's why they change it when it starts raining.
Exactly, right? So they have no tread at all because it's just cheaper to make, and because they're going through tires lots, right? And the surface area is more about the pressure. Because they're wider, there's not as much pressure, and so they don't heat up as much, so they don't degrade as much. They could be skinny, but then they would be much hotter. And they'd be less massive too, right? So they kind of have to strike that balance as well. Lots of sort of things at play here. And last one, starting or sliding friction is directly proportional. What does that mean? To the force pressing the two surfaces together. And it doesn't mean equal. Directly proportional means if the force gets bigger, the friction gets bigger, right?
It's equal. More like on a sprayer.
Not equal, but.
Where they have those big wide tires? Yeah. Those, I think that, isn't that not saying more designed so that there's not as much tire knocking down plants?
Plants go in between the rows,
Right.
but I'm just saying, it doesn't follow that rule.
Well, sprayer, I don't know how fast you're driving your sprayer, I've never driven one. I don't imagine they're going fast. And
Well,
they're
they can, though.
I'm sure they- Yeah, I'm sure they can.
They're pretty fun,
Yeah.
actually.
But you're on land, you're not on asphalt or anything, right? So I don't think that the heat on the tires would be that
Unless you're
significant.
looking at the highway.
That's a good question. Yeah, I think more is it so that they stay above the crop, right?
But it's, you said if it's bigger, it's of course bigger.
Oh, okay, I hear what you're saying.
You've got small tires, so they make it
Right.
bigger.
Yeah, but what if you had a sprayer, a full sprayer, full of chemical, and the field is soft? You sink, right? If you had the big wide tires, you wouldn't sink as much, right? Like the tracks that are on the new tires, they don't, or the new tractors, they don't sink as much because they're wider. It's got more to do with the pressure. I was thinking more about those really massive drag tires that are really big, right? Compared to if they were really narrow, they'd be much less, the narrow ones are much less massive, right? Right? There's also, I should say this too. Let's go back to here. Neither one of these is rolling friction. Rolling friction is actually fairly complex. Okay? Everything that we're going to be dealing with motion is going to be dealing with sliding friction. Okay. This you need to write down. If you haven't written anything down, you need to write this one down. Did I hand out the sample questions? I don't think I did. Hang on. Those of you looking for a place to write down could probably just write on this. Yeah. If you haven't been writing stuff down, I would suggest you write it right on here. So this is a brand new formula. It's not really one
For a second.
that you can derive.
Coach now saying, I just can't interrupt you when I'm doing drills next time.
Apparently not, they say in Greek.
Yeah. That's how it's, yeah.
Is that right? So this letter right here, Cole. This letter right here, Cole, is the Greek letter mu. Mu. It's like a U. It's kind of got a tail up in the front. I'm told that in Greece it's pronounced me, although I did go online, I researched a little bit. I can't find a scientist anywhere in the English-speaking world that says it differently than mu. It is a Greek letter, and I've often wondered, what do Greek grade 11 physics students learn about this? Do they use, because it's the Greek letter M, so what do they use? Because they would have the Greek letter F and the Greek letter F there, right? So I wanted to stop and ask some high school kids when I was in Athens, but my wife said it was weird and I wasn't allowed to.
Well, right, because like, we use our language, but then that's like the symbol for it.
Right, so in their language,
It would just be an M.
it'd just be their M.
Oh, maybe they use our M.
I don't know, maybe. I'd like to know. Wouldn't you like to know?
Yeah.
Hey, that's a good question.
Random Greek phone number.
A random Greek phone number.
Oh, yeah.
Just ask them.
Be like, hey,
when you guys.
And throw in some souvlaki. Yeah.
Wait, I have to, write it.
Good point. Okay, so mu is what's called the coefficient of friction. And it is the ratio of the force of sliding friction to the normal force. So it is, mu is FF over Fn. The ratio is 1 divided by the other. Friction force divided by normal force. What are the units for mu, do you think? No, the units. Like, what are the, like, meters or kilograms or seconds? Well, what's the unit for the top here? Friction force is in newtons. And the friction force for the bottom is, can you cancel units? Yup. And so, Cole, the unit for mu is nothing. There is no units. There is no units. It's not mu's.
It's literally just a pointless letter.
No, it is a number that tells you how much bigger the friction force is compared to the normal force. But it is not a quantity, it is a ratio. So there is no units for mu. Okay, so I have 3 samples here for you. So let's see mu in action. And I've provided you with the sample question. A box with a mass of 175 kilograms pulled along a level floor with a constant velocity. If the coefficient of friction between the box and the floor is 0.34, what horizontal force is exerted in pulling the box? There's a couple key words here. Constant velocity. What does that mean?
V bar equals 0, not slowing down.
Not slowing down, not speeding up. From a force standpoint, it means that the forces are equal or balanced. Let's draw a free body diagram. Okay? We have it's pulled along a level floor. So we have an applied force, Fa. Ty, you need to let Cole watch. And then you need to reciprocate by actually watching, Cole. And you also have a friction force. And those forces are? How do I know they're equal? Constant velocity. Leo. Okay. The only 2 things that I have in the problem are the mu value I can't talk over you today. The only 2 values that I have are the mass and the mu. But I have one more. I have G is minus 9.8. Whoa, hold on here. I thought constant velocity. Well, this minus 9.8 isn't necessarily meters per second squared. It's really 9.8 newtons per kilogram. Remember they're one and the same? And not only that, but that minus 9.8 is actually the weight force. It's down. So the constant velocity is horizontal, but up and down, the constant velocity is 0. It's not accelerating up and down at all, is it? And that is Fm. Meters per second squared and newtons per kilogram are equivalent units. They're equal. Okay, so from my mu value, mu equals Ff over Fn. Don't write it down yet. Maybe you did already. How much is the normal force? Well, it's opposite the weight force. Do I know the weight force? No, I don't, but I can figure it out, can I? So that's actually the first thing to do. No, it's mass times gravity. It's the mass, 175 times minus 9.8.
Minus
175 times 9.8. 1715. Negative 1715, that's right. And therefore, the normal force is positive 1715 because it's equal and opposite, right? The normal force is up, Fn. Newtons, correct, Brett. And now this 1715 can be plugged in over here. Just going to make myself a little bit more room. And the mu2, so 0.34 is equal to, notice how I'm separating my steps, and I'm lining up my equal signs, and I'm showing my work. So for friction force, the normal force is that 1715. And how do I solve that for FF?
you multiply.
Multiply both sides, and you get 0.34 times 1715.
500.
583.1. That's the friction force. But the question asks, what horizontal force is exerted in pulling the box? What is, we're trying to find the FA. But because it's a constant velocity, therefore, the FA and the FF are equal to each other. Exactly. Right? Therefore, the applied force is 583.1.
Breeze.
583.1. So if you think about a car driving down the highway at a constant speed, it's on cruise control, and the car weighs 175 kilograms, right? It's moving at a constant speed. The engine would have to produce 583 newtons of force to overcome the friction, right? Just to keep it going at that constant speed. Example number 2 says, a box with a mass of 100 kilograms accelerated by a force of 200 newtons across a level floor. If the coefficient of friction between the box and the floor is 0.2, what is the overall acceleration of the box? So this is very similar to a question you've done already. It just, instead of me giving you the friction force, now I'm giving you the coefficient of friction. I'm making you do that one step. Should we draw the picture? Applied, oh, now this time there's an acceleration, so that means what? It means that the applied force is considerably bigger. Still got weight force, still got normal force. FA.
Why did you find the FF?
On the last one?
Yeah.
Because it's a constant velocity, the FF, I multiplied here, right?
Oh, yeah.
Right? So basically, I'm kind of doing the same question just backwards here. Right? Okay. Generally, with any of these questions, your first step is going to be find that weight force, find the force of gravity down by taking the mass, 100 times gravity minus 9.8 minus 980, making the normal force equal to positive 980. Question. Okay, so that's my normal force. Now I'm going to go what? What's the next step? Same as the last one. Mu is FF over Fn. Mu value is 0.2. Solve for friction force. Fn 980. Nope, because I swapped it, because the weight force is down, negative, but it's actually, mu is actually FF over Fn, and so they're equal and opposite saying, so the Fn is up, it's positive. Yep. Again, solve by multiplying. So take that 980 times 0.2, 196 of friction. Now you got to take this and you got to apply it to this picture here. Right? We're looking for the overall acceleration of the box. Now I have a horizontal net force. Right? I have an F net X if you want. Right? A horizontal net force. And that's going to be made up of the applied force plus the friction force. And how much is my applied force? 200. Plus, how much is my friction force? 196. Now, I made sure I made an error. Plus a negative. Right? Why is it negative 196? Because it's moving the opposite way. Do you get the negative out of this? No, you have to make it negative by looking at the picture. You have to assign it a direction. If you don't do that, you're gonna end up with 396 here, and you're increasing your applied force. That doesn't make sense. Yeah. This is gonna make the net force only 4. And now the overall acceleration. F net is equal to ma. 4 is equal to the mass, 100a. How do you solve that? That's 100 times a, so we're going to have to divide by 100. 0.04 meters per second squared. How many marks do you think? 4. Yeah.
You do the test out of a 4 question. It's like, oh, it should really be 2 marks.
I hate when I do that.
So everyone was just freaking out. And he's like, oh, sorry, should have been.
Sometimes it happens. We make mistakes. I think I'm going to leave it there today. You guys have the third example, right? Shall I leave that one for tomorrow?